Journey to the largest star. When we look at the sky in the evening, we see a spiral of light. Throughout history, people have always wondered and researched these luminous objects. These objects, which appear at night, disappear as the sun rises during the day. People have named these objects over time. As a result, names such as stars, planets, comets have emerged. Stars are giant spheres of plasma that generally contain hydrogen and helium. Galaxies are formed when stars come together. When we look at the sky with naked eye in the evening, it's possible to see approximately 6,000 stars. The closest star to the Earth is the Sun, which is the energy and life source of the Earth. The Sun provides the necessary energy for the Earth. Other stars appear in the sky when they are not affected by the sunlight. Stars are not visible during the day due to the effect of sunlight. The reason why stars shine is that the energy released in the nuclear fusion reactions occurring in their cores is emitted by outer space radiation after passing through the star. Fusion is the release of energy and helium as a result of the fusion of hydrogen nuclei. Stars fuse millions of tons of hydrogen nuclei every second, releasing energy and helium. For this reason, stars have dense hydrogen and helium. When we look at the sky in the evening, the 6,000 stars we see make up very little of the total stars. There are about 200 billion stars in our galaxy, the Milky Way. In the universe, there are about 100 billion galaxies like our galaxy. Using various instruments and computational methods, astronomers can determine the age, chemical composition, and many other properties of stars. The most important factor in the development process and the formation of the end of a star is the mass of the star. By looking at the development process of a star, the diameter, rotation, and temperature of the star are determined. The Hertzsprung-Russell diagram, in which stars are marked according to their temperature and brightness, is used to determine the development process of stars. Stars contain a lot of hydrogen, some helium, and very little heavy matter in their structures at a young age. After the stellar core is sufficiently condensed, some of the hydrogen in it is continuously converted to helium by nuclear fusion reaction. The remainder of the star carries the released energy away from the core by a combination of radiation and convection. These processes prevent the star from collapsing inward, and the energy is radiated into outer space, creating a stellar wind at the stellar surface. After the hydrogen fuel in the core is depleted, stars with a mass of at least 2/5 of the Sun's mass expand to become a red object, with the heavier elements fusing in around the core as a crust. Some of the matter is then ejected into the interstellar medium, forming a new generation of stars in which the heavier elements will be denser. The collapse of the star into the interior occurs when the heavier elements become more and more. To put it briefly, the death of the star has occurred. In systems consisting of two or more stars, there are stars that are gravitationally bound together and usually orbit each other in regular orbits. The interaction of the gravitational force of stars that orbit very close to each other has a significant effect on their evolutionary development. The largest known star. Astronomers who have been working on stars for centuries have determined the existence of stars of different masses. Stars with 93 times the mass of Jupiter have been detected, with stars tens of times more massive than the Sun. The largest star detected is Eta Carinae. Eta Carinae is a star system located in the constellation Carina. The distance of this star from us is approximately 7,500 light-years. It has been determined that the first component of the star, which consists of two components, is about 150 solar masses, and the second component is about 30 solar masses. Currently, the combined volumetric luminosity is 5 million times that of the Sun. It is the largest star that can be studied in a relative detail today. The other component is optically impossible to see due to the large and thick red nebula surrounding Eta Carinae. However, a hot supergiant with 30 solar masses is known to be in orbit around the primary. In 1820, Eta Carinae began to shine for an unknown reason. Its brilliance increased day by day. In April 1843, its brightness increased a lot and became the second brightest star. The surrounding Homunculus Nebula is thought to have formed during this eruption. Visible purple light reflected from Eta Coronei can be seen in the center of the nebula. Eta Coronei is still experiencing unexpected eruptions. Its massive mass and variability make it a majestic supernova candidate that could explode in the next few million years. The first component of the star, which has 150 solar masses, exceeds the Eddington limit. However, because it has sufficient mass, the star remains intact. According to the Eddington limit, a star can have a mass up to 120 times the mass of the Sun. Since our subject is a bright giant, it would be good to look at some principles first for a deeper understanding of the subject. Bright supergiants have two key features: great mass loss and great luminous power. At first glance, cold bright giants appear to be mingling with bright blue variable stars. Stellar evolution plays a key role at this stage, clearing up the confusion. The difference between bright supergiants is due to the different masses of the stars. Massive stars are subject to great gravitational forces. In order to overcome the gravitational force, the star has a greater temperature and, as a result, greater luminosity. While the gravitational force is active throughout the star's life, it's not the only force at work in the star's energy production. If that were the case, gravitational energy production in a Sun-like star would take 100 million years. In the 1950s, it was understood that nuclear reactions played a large part in the energy production of stars. A Sun-like star lives on the main sequence for 10 billion years. The star produced an opposite force to counter gravitational force by converting hydrogen into helium in a controlled manner in its core with nuclear reactions. This is important for the survival of the star. Eta Coronei's star consumes more fuel than the other stars, causing it to produce more light and heat. Eta Coronei consumes more hydrogen and generates energy with more helium to keep its mass in balance. As a result, its brightness reaches millions of times that of the Sun. It also forms a star position with temperatures greater than the Sun.